Hello, this is Roger from the Virtual Technology and Design Laboratory, and in this tutorial, I'm going to walk you through how to use GDAL to process DEM terrain height maps for Unity. As I mentioned in the previous tutorial, the process is based on this blog by Alistair Atkinson, and I will be loosely referencing it as we go along. The first step is to acquire a digital elevation map of the area you would like to represent. In this folder, I have a DEM of Lower Russian River Lake. I've used Python to embed the bathymetry data of the lake into the surrounding area. When we look at the Explorer, the thumbnail is completely white except for the lower left corner. Also, when I open it up, we can see that's completely white except for the lower left corner. So what is going on here? This is basically because despite the fact that it's a TIFF file, a .tif, it's not an ordinary image. Instead of containing red, green, and blue byte values or 8-bit values for every pixel of the image representing the color of a pixel, like you'd have in a normal color image, each pixel contains 32-bit floating point value for every pixel. The Windows Photoshop viewer doesn't know how to read these 32-bit float values, and rather tries to read the 32-bit float values as RGBA values, and this is basically what gets rendered. So the lower left is zero floating point values because there's no data there, and that basically gets read as black. So after we've acquired the DEM, we probably want to go about checking to make sure that it actually represents what we need it to represent. And we can start this process by using GDAL info to identify the location, projection, and the band statistics of the map. So what we can do is inside of our folder, we can hold down Shift and right click, and this brings up the option to Actually, let me try that again. Shift and right click, and that brings the option to open the command window here. So we can see that this command prompt is at the location or inside the same folder as our height map. So if we type dir, then we can see our height map is in here. Then we can use GDAL info by typing GDAL info and then the name of the file that we would like to get information on. So if I type GDAL info space rrlake underscore dem.tif, and you can use tab to autocomplete as you're typing a path of a file. We can see that this is a geotiff file. We can see the name. We can see the size is 1025 by 1025. That's convenient since GDAL needs a power of 2 plus 1 data file. We can also see that the transform is Albers conformal conic equal area transform that and has a unit meters. This is good because if this was in degrees, then we might want to reproject this so that it's in meters. This will keep the scale of the virtual world consistent and make it easier to place objects at known locations. If you want to or need to reproject from degrees to meters, then you would use GDAL warp, which is documented here. And hopefully by the time that you go through this tutorial, using GDAL warp won't be as intimidating as it first appears. All the GDAL executables kind of have a similar feel, and once you sort of like learn how to decipher the parameters and how to specify them, it's not as bad as it looks. Alright, so if we go back to our command prompt, we can see a lot of information, but what is actually missing is statistics on the elevation data, or the elevation. So we can actually get that by typing -stats at the end, and this basically tells it that we want it to compute the statistics and display the statistics for the bands in the data set. So now down here we can see that band 1 contains float 32 data, so 32-bit floating point numbers. And we can also see that the minimum is 0, the maximum is 13,366, and the mean is 600. So 0 corresponds to that dark black corner, and the maximum value is 1,336 meters. So this can be helpful to identify the units of our map and to figure out how we want to scale the elevation map. So if we want an even better representation of the data set, we have several options. We could use a desktop GIS application like ArcMap or QGIS. We could also use the micro DEM application that Alistair recommends in his blog post. We could also use the GDAL libraries for Python to open the dataset and use matplotlib to visualize the contents. Another quick and simple option is to use GDAL DEM, another executable program provided as part of GDAL, to visualize the digital elevation map as a hillshade. GDAL DM can actually create several different types of visualizations for DEM aside from hillshades. But if we want a hillshade, then we would specify a hillshade parameter, or a keyword, I guess, and then we specify the name of the input DM and the output hillshade. So that would look like GDAL DEM hillshade, then the name of our input map and our output map. And then if we look back at the help page, all these other options that are in square brackets are optional, and so we don't really need to worry about them at this point. If I hit enter, this is telling me the progress as it completes. This is a pretty small file, so it's more or less instantaneous. And then if we look in our folder, we can actually see the resulting map. We can see there's a fair amount of banding in this dataset. That's what these lines are from. This sort of artifacting can occur when a dataset is warped from one projection to another. The interpolation methods that you use can help to avoid such warping. Unfortunately, when this dataset was warped, those options weren't looked at all that closely, maybe. I didn't do it. But, you know, sometimes that's how it is, and once it's actually in there, this is not very noticeable, so we should be fine. So now that we've validated the dataset, we can move forward to building a height map for Unity. Graphics programs like Unity or 3ds Max, or you know, Blender or what have you, use height maps and displacement maps to specify gridded geometry of objects. One of the simplest and most standard file formats for height maps is a .raw file, .raw file. This contains just the binary data values of the grid without any extraneous metadata. That includes metadata that conveys the width and height of a grid. Height maps are generally normalized and are 8-bit or 16-bit. 8-bit height maps can only represent 256 distinct levels of heights. A 16-bit height map can represent 2 to the 16 or 65,536 unique levels. This is important because if we have a lot of vertical elevation, say 1,300 meters like we have in this map, and we can only have 256 distinct levels, that means that each level is separated by 5 meters, and if we process it to only have 8-bit resolution, which by the way is what you get if you use ArcMap. There might be a better way to get ArcMap to spit out a 16-bit file, but I haven't figured out how to do that, and I wouldn't claim to be an ArcMap expert. But in any case, if you do that, then you end up getting something that looks like terrace agriculture. So there's a kind of a severe staircase effect, and your terrain ends up looking like this, even if it's actually smooth. So we can get around that by using 16-bit height maps, and because we basically have 65,536 different unique levels, the resolution or the difference between each level ends up being about 2 centimeters in this case, which hopefully you can see how that would avoid this sort of staircase effect. So how do we go about converting our TIFF DEM to a normalized raw? Well, we'll want to use GDAL Translate. Here's a page for GDAL Translate. And there's a whole series of options to scale there's a whole series of options to specify different parameters. Luckily, we don't need to use every single one of these. We can see here that -OT specifies the output type, and there's several different types here. So there's byte, int 16, uint16, uint32, so on and so forth. Right now, it's a float 32, and we actually want to convert it to a uint16. Why uint16? This is because we want it to be unsigned 16-bit integers. Each integer is represented by 16 bits, or ones and zeros, and we only want to represent 0 and positive whole numbers. We don't need to represent negative numbers. That lets us represent numbers between 0 and 65,535. If there were a sign, then we'd have to use one of our 16 bits to represent the sign, and then we could represent negative numbers from negative 32,768, that's 2 to the 15, to positive 2 to the 15. So that's probably more detailed than you need to know, but basically what that means is when we're at the command prompt, we'll need to type GDAL Translate OT to specify the output type, and then specify the output type as uint16. I don't believe this is case sensitive here. We could do it this way. Alright, so next we need to specify the scale. So right now, our band represents elevation data in meters from 0 to 1336. We want to normalize it so that we're using most of the range between 0 and 65,535. So we need to specify the minimum. So we're going to use scale, which is here. And then we need to specify the minimum of the source and the maximum of the source. This basically specifies like the values that it gets clamped at. So if you say we put 1,000 as the source max, any value over 1,000 it would just treat as 1,000. And then we can specify in the units of the output format the corresponding values for the minimum and maximum. So in the original, the source min scales to the destination min value, and the source max scales to the destination max linearly between those two. For this example, the source min is 0, and for the source max, I'll specify 1,400 meters. This is a nice round number that we can use later inside of Unity. and it gives us some room if we want to sculpt the terrain or deform it to represent snowpack or something along those lines. Then for the destination, min and max will have 0, and then 65535. That is 2 to the 16 minus 1, basically. So then I need to specify that the output format should be a raw file, and for GDAL that means that we need to do .of envi. That tells it to use the envi driver. I'm not exactly sure what that means, but basically means that it'll get a raw file out of it. So then lastly, we can specify the source dataset name and the destination dataset name. So in this case, the source is rrlake_dem.tif, and we'll want the destination to be rrlake_dem.raw. And I'll hit enter, and it ran through. So then inside of here, we can see that it created this rrlake_dem.raw. If I go to properties, we can see that the size is 2 megabytes. So let's do it in here. So we can see that the size is 2,101,250 bytes. So inside of here, if we do 1025 times 1025 times, so 16 bits is 2 bytes, because a byte is an 8-bit word, times 2, then we get exactly that number, 2,101,250. So that's not something that you need to check, but that's just to illustrate the point that it's packed the data into this in a binary form into this file, where each pixel is now represented by 16 ones or 1 or zeros or 2 bytes. So at this point, what we probably want to do is make some notes so that we know what is represented by that raw file, since it doesn't contain any metadata. And if we're handing this off to someone else to build the Unity part, they may not know what exactly this is representing. So inside of here, I'm just going to create a text file that's called rrlake_dem.raw. Yeah, text is fine. Alright, and so inside of here, I just want to make a note that rrlake_dem.raw represents Lower Russian River Lake. Let's say resolution between pixels is this number. So I can right click and then click mark, highlight this, then hit enter to copy, paste that in there. Meters. Area of map is 1025 times that number. So the map is Map is 6248.41 to 5 meters square. Or by, okay. Height is normalized between 0 and 1400 meters. So this will be critical, well, this will be critical information that we need to know when we set it up inside of Unity. So now we can go ahead and open Unity. And then inside of the hierarchy, I'm going to right-click, go to 3D Object, and then Terrain. And then I'm also going to go ahead and move my file into the assets folder. I guess I don't have to do it that way. I can just drag it directly into here. So my raw file and the text file are in my assets folder now. Then I'll click on my terrain and then over in my inspector and click on the gear, and then down here there's this import raw option. I can find my .raw, click open. So it's basically identified the depth as 16-bit and the width and height as 1025 by 1025. I actually do want to flip this vertically, and then here I want to specify the values that were inside of here. So the map area is 1648.4125. And then the Y is 1400 meters. And then I'll hit import. So let me flip around so we're oriented with our z-axis up or north up. And then over here, I actually want to bring my pixel air down to 1, and then I'm gonna bring down the lighting a bit so we can get an idea of what's going on here. So now we can kind of compare this against our hillshade to make sure that things didn't get flipped around during this process. So here's our hillshade. And here's our height map. And it looks like it is correctly oriented. This one is a little bit easier to figure out because we have this thing here. But when I did this, I did the flip vertical, and that made it so it imported in the correct direction. If you don't do that, then it might come in not flip the way that you want it, and then you on Alistair's page there's like a little script that would rotate it for you. Another option is to do that inside of Python and then produce the raw file that's like rotated the way that you need it. But if you follow the steps, then it should come out correctly at this point. So that's basically how you get data or DEM data into Unity. Thank you for watching. I hope you found this useful.